Welcome to this first lecture on waves and oscillation. My name is Daniel Maitredia, and I will be taking you in this course known as Waves and Oscillation SPH 3153. Now, before we start the first lecture, I would like to pass some information pertaining this course. Number one, as you know, the running materials will be posted in the RMS system, and this will include the notes, links to appropriate video lectures, the assignments, any relevant information. You will be able to find it in the RMS system. The next piece of information I would like to convey is the practical sessions. If you were in campus, this course was supposed to be done even using practical sessions. But unfortunately, we are not able to undertake that part until maybe a time when you will be able to come to the university and take the practical sessions. But what I will try to do is incorporate an aspect where we will be doing some programming and simulations involving the subjects and the problems that we will be discussing in this lecture. So we will be using a computer to kind of solve those problems. And the way we do that is we have to start by running a programming language. In this case, we will use Python programming language. It's a very popular programming language used in the scientific communities. All you need to install Python is available online. So Python is an open source programming language, meaning that you don't have to pay for the software, for the software to learn the program. You just need to download appropriate packages and install. And what I'll be doing is I'll be sharing some video sessions on how you what you need to do to install the appropriate software for you to be ready to start programming in Python. So watch out for those video tutorials instructing you on how to install the relevant Python package. In this case, there's a specific Python package that we call Anaconda. That is what I will be recommending that you install, and I will share a video on how to install Anaconda in your computer. I hope everyone is in a position of a computer so that you can be able to install and start programming. In any case, at your stage, I think it will be very wise to start programming this stage, so that by the time you reach the upper years, the third year and fourth year, you are quite proficient in computer programming and general computational tasks. That is very important even in the job market. So please watch out for that, and make sure that once an assignment is given, a computational assignment is given, you try and do it well. So RMS is a resource you need to be constantly checking for the materials I will be uploading, the assignments, and the assignments go with the due dates for submission. The class attendance list also is required on weekly basis. So yeah, so such things found in the RMS. Now, so that is the information I wanted to start sharing before we embark on our course. And our course comprises of the following topics. We'll start by doing high school review of waves. You know, this is not the first time you are discussing waves. In high school physics, you looked at waves to some extent, to some depth. And so we want to just review so that that forms a good prerequisite of the material we will be discussing going forward. So that becomes basically our first topic. We may not be able to review everything, but we will brush over the waves, the high school waves topic. Then we will start discussing a very important concept known as the simple harmonic motion. In physics, simple harmonic motion and harmonic motion in general is very commonly it appears every now and then in different units in upper years. So we need to first of all understand what it is. Then we progress on and look at damped oscillations and forced oscillations and resonance and superposition. All these are different aspects of waves and oscillations. We will be discussing more when we get there. Next, can I move on? Yeah. We look at progressive waves and standing waves and refraction and transmission of waves. So those will be the topics that we will be looking at. And we start by looking at what we mean by waves and oscillations. So let's start with oscillations. What do we mean by the term oscillation? Basically, oscillation is a very common term, not very different from the English meaning of oscillation, which is basically that phenomenon where you have body moving back and forth. So it's a repetitive motion. That's an oscillation. So we can say in literal technical terms, an oscillation is a process in which a physical quantity changes periodically for a period of time. These include movements that occur periodically around an idle position. So the main thing here is you have a physical quantity changing periodically with respect to time. And this physical quantity we are talking of could be position. For example, if you have a pendulum moving back and forth, that pendulum is oscillating. And so what quantity in the pendulum is changing? It is its position. Its position is changing periodically. It's following a periodic motion. It's a regular, repetitive motion. That is an oscillation. Harmonic vibration refers to that vibration that is sinusoidal in nature, and the sinusoidal is a pattern which follows the mathematical sine and cosine waveforms. So an harmonic vibration can be described using sinusoidal functions, that is the sines and cosines. Okay. Then we look at the waves. And before we discuss what waves are, it is important to say that often when you have a body undergoing some oscillation, then that is where waves emanate from, and then they travel. So the oscillations are linked to generation or the production of the waves, and then the waves now propagate in space. So then we can say a wave is a spatial and if you like, and temporal periodic process in which energy, but not matter, is transported. So it's a process in which energy is transported, but not mass. It's only energy that is transported. The direction of energy propagation is called wavelength. The perpendicular to the wavelength runs the wavefront. The wavefront is the geometric location of all the particles that belong to the same phase. So what we are saying is a wave transports energy without transporting matter. So you have energy propagating forward, but the oscillating particles don't really move from their mean position. They just vibrate from their mean position, but they don't travel with the wave. They are left at their mean position. So that's how we can describe a wave. So some of the terminologies that you came across in high school when describing a wave included a term like amplitude. What is an amplitude of a wave? It's the maximum displacement of an oscillating particle from its mean position The SI unit is meter. You can measure an amplitude in meters if you want to stick to SI unit. So, and there is a diagram down there showing you what an amplitude is. Basically, is that distance from the mean position, the zero position, to the maximum point where the particles that are oscillating can reach. You know, we are assuming that this wave is moving due to as a result of some particles oscillating about their mean position. So the maximum displacement from the mean position of the particle is what we are referring to as the amplitude. We also have another terminology that we refer to as the wavelength, and it is now the spatial distance between two successive particles oscillating in phase. Now, you can see the diagram where one wavelength is indicated. Now, you can take any point along that wave pattern as long as you can trace from one point to the next point that are in phase, then you have a wavelength. So I don't know if you can see my cursor. So we could start measuring our wavelength from this point. You see the wave, the wave is at this point is moving downwards. So a wave would start from, a wavelength would start from this point all the way to this point. So from here to here is also a wavelength. You could also say from this point to this point is also forms a wavelength. So it depends on which point your reference starting point is, and then you have to move until you trace the next point in phase with the starting point, and that distance makes a wavelength. So it's not a new concept. So I want to believe you are at home with that explanation. Now, the next terminology is the period of a wave, and it is defined as the time taken to cover one complete oscillation. It's also measured in seconds if we are to stick with SI units. Now, what I needed to emphasize here is that wavelength is denoted by a symbol, a Greek symbol known as lambda. So lambda is a symbol that denotes wavelength in waves, and we shall be seeing lambda a lot as we progress. So please, I am sure you know that symbol, how it looks like. So don't be surprised when we encounter it. While I was making the diagram, I forgot to include it, but we will come across it in due time. So the next thing we want to look at is the frequency, which is what? It is the number of oscillations per unit time, or the number of oscillations in 1 second. All those are the terms, all those are definitions of the frequency. It's measured in hertz. 1 hertz is equal to 1 oscillation in 1 second. Then we also talk of wave velocity. This is the speed that the wave is traveling in the specified direction. And how do you compute the wave velocity? You multiply you wave velocity, you divide the wavelength with the period. So basically, you use the simple formula that velocity or speed is distance over time, and the distance here we are talking of wavelength, and time we are talking of period. So it is the wavelength or lambda over period. But you realize that there is also another relationship between frequency and period. As you could be remembering from high school physics, what is the relationship between frequency and period? Frequency is equal to the reciprocal of the period. So if then we are saying frequency is equal to the reciprocal of period, then we can say the wave velocity, which we are saying is equal to wavelength over period, then we can also say it is equal to wavelength multiplied by frequency. We are going to be encountering such a relationship going forward. So please note that. Now, this something also that keeps popping up while we are describing waves, and that is the phase difference. And you can now start talking of the phase when you are referring to one wave in comparison to another waveform. So like you have more than one waveform traveling, then you might now start wondering, talking about the phase. If you have two waves that start the same time and move with the same speed, then we say the two waves are in phase. They are starting the same time, same position, and they are moving with the same speed. So they will, all of them will be oscillating in sync. They will be in sync. When particles at a specific position, at a given position, are moving, they are all moving in the same direction, up and down. So we say such waves are in phase when the oscillating particles move in sync. All of them are moving at the same rate, at the same position. But when one is moving up and another one is moving, so they are not in synchrony, then we say they are out of phase. And if you look at the waveform, it's like the two waves are not moving in a phase, so to speak. They are out of phase. And to quantify the extent at which they are out of phase, then we start talking of phase difference. What is the phase difference? Sometimes we will talk of phase angle. They are out of phase by this angle. So that's what we mean by phase, is if the two waveforms that we are interested in discussing about are moving in, they are at sync, they are moving in harmony with each other, then we say they are in phase. But when they are not, when one is either moving faster than the other one, or one begins earlier than the other one, then we say they are out of phase, and you can measure the phase difference using a term we call phase angle. And we shall be also been discussing much of a phase angle in our subsequent discussions. So up to there, you understand that this was basically high school physics of waves. So there isn't much that is new in that discussion. In fact, there is a lot that is not captured. And so you can try to check your, to polish your understanding of waves by answering the following questions. Basically, what I needed to say is that waves come in different types. Broadly speaking, we can say we can categorize waves as either mechanical or electromagnetic waves. So you could have mechanical waves or you could have electromagnetic waves. Mechanical waves are things like sound, the ocean waves, water waves, and such things. Electromagnetic waves are things like the light, visible light that we use to see, things like radio waves that we make use of when we are making phone calls, when we want to communicate with the people who are far away, or when we want to get a television signal. So those are examples of radio waves. We have other waves that we call X-rays and gamma waves. We use these mostly in medical imaging, medical diagnosis, and material processing. Yeah, so we also have an electromagnetic wave known as microwave and UV. Again, they find application in different places, but there are different forms of electromagnetic waves. Infrared is also there. So in high school, you encountered what we called the electromagnetic spectra. You know, you can arrange the electromagnetic waves and depending on their frequencies or wavelengths, so that the shortest wavelength electromagnetic wave is what? Gamma, followed by X-rays, followed by UV, followed by visible light, followed by infrared, followed by microwave, followed by radio waves. That's the electromagnetic spectrum. So these are things I believe you encountered in high school. So that in that question, what it is testing is what? Which portion of the electromagnetic spectrum is used in television? Simple. Question number 2, when red light is compared with violet light, Both have the same frequency. Is that so? Both have the same wavelength. Is that so? Both have the same speed. Is that so? Red and light travel faster than violet. Is that true? Again, at your level, you should be able to answer that. If you know the wavelength of any form of electromagnetic radiation, you can determine its frequency because, again, you are given a multiple choice. You try to see if you can answer that. Now, the next question is, what is the frequency of infrared of 1.0 times 10 power negative 4 meters wavelength? So now again, you are supposed to use some relationship between frequency and wavelength to work out that problem. Okay, that forms our review of high school physics, and we are about to start university physics. And as you know, university physics can have a lot of mathematics. And so we review some concepts in maths that we will be making use of, we will be relying on as we try to discuss the waves, this course, waves and vibration. One concept that we will be making use of is the complex numbers. And complex numbers, I don't know whether you have been introduced to them, but complex numbers have real and imaginary parts. So if you are given a complex number, you need to identify both the real part and the complex part. And I have shown you there, you have been given a complex number, Z, and it comes with the real part, which is X, and the imaginary part, which is Y. And the way you know the real and the imaginary part is because the imaginary part is also accompanied by the imaginary number I. I is basically the square root of -1. Okay, so if you see a number that has a coefficient of I, then you know that is the imaginary part of the complex number. And when you see the other part without the imaginary number, then you know that is the real part. And I've given examples down there, 3 examples. So the first one is we have sent equal to 3 plus 4i. And you might be asked, which is the real part? It is 3. And the imaginary part is 4. In the second example, we have z equal to 5.2 plus I. So the real part is 5.2 and the imaginary part is 1. We got another complex number, z equals 2 minus 3j. The real part is 2, the imaginary part is minus 3. So that's one way of presenting complex numbers. That is one way of presenting complex numbers. And I need to note that this notation is commonly used, but there is also another notation of presenting complex numbers. What I need to say is, in a complex number, you might be asked for the a complex number has got two information, two types of information. It has got what we call the magnitude information, and it has got the phase information. So I forgot to indicate how you work out the magnitude and phase of a complex number given in this notation. And so please find out for yourselves. If I give you a complex number like the ones I've given you, how would you get it phase? How would you get it magnitude? Please find out. So we proceed. No, I didn't forget. It's there, it's there. So the next slide looks at the magnitude and phase of complex numbers. So how do you get the magnitude of a complex number? So the magnitude of a complex number, if we are talking of magnitude, then we denote it by putting the complex number between two vertical bars. If you like to send surrounded by two vertical bars, then we understand that you are talking of the magnitude of the number. And it is basically the real part squared plus the imaginary part squared, then get the square root of the sum. Okay, simple. So you need to ask yourself, what is the real part of that complex number? What is the complex part of that complex number? So square them, get the sum, then get the square root of the sum. That gives you the magnitude. Phase. Remember I said a complex number carries two pieces of information. There's the magnitude and then the phase. So how do you get the phase of a complex number? You get the arctan of the imaginary part of that number. You get the arctan of the ratio of the imaginary part to the real part. What I'm saying is, get the tan inverse. Arctan is basically tan inverse. We are more used in the term tan inverse. So get the tan inverse of y over x, where y is the imaginary part of your complex number and x is the real part of the complex number. Okay, remember that was one way, that was one notation of denoting complex numbers. This way, where you put the real part plus the imaginary part. But there is also another way you can present complex numbers using the exponential notation. Here, you need to denote a complex number by its magnitude and phase. So then we say the complex number is equal to the magnitude. Remember, the magnitude is that term that is surrounded by two vertical bars multiplied by exponential. E is the exponential function. I want to believe that you understand what an exponential function is. So is the magnitude of the complex number multiplied by exponential is to I, the imaginary number, and the phase. Remember, we have previously seen how to compute the magnitude of the complex number and how to compute the phase of the complex number. So it's possible I can give you a complex number like one of these given in the example here and tell you to convert it in the exponential notation to represent it using the exponential notation. In that case, you'll need to compute the magnitude and the phase, then use this notation where you say send now is the magnitude multiplied by exponential I, then the phase. Now, this is a formula we call Euler's formula. Euler, sometimes some people will call it Euler formula, doesn't matter. Tells you, Euler's formula tells you that E raised to power negative I phi is equal to cos phi plus I sin phi. Is that so? I'm not sure. I might miseducate you. I will need to check, but where my confusion is whether E is raised to negative or that negative is there. But let's proceed. So what we are saying is, if you are given a complex number in the exponential notation, the way you know the real part is you say the real part is equal to the magnitude of the number multiplied by cos phi, and the imaginary number is equal to, sorry, what am I saying? The real part of the complex number written in the exponential notation is equal to the magnitude multiplied by cos phi. That is the real part. And the imaginary part is the magnitude multiplied by sin phi. And those relations are as a consequence of the Euler's formula. So we are almost closing up. But when we are talking of complex numbers, we cannot stop until we also talk of complex conjugate of a number. Every complex number has got its complex conjugate. And so if you are given a complex number like you are given here, the first equation, then its complex conjugate is denoted in the second, or is shown in the second equation. Now, see the complex conjugate send has got a wave on top of send, or attained is, I think, let's call it a wave on top. And also its complex conjugate, the magnitude is the same. The magnitude is the same as the complex number. Its complex conjugate magnitude is the same. What changes is the sign of the phase, so that if the phase was positive, Now the complex conjugate phase will be negative. Okay, that's the difference. And you need to be able to also write the complex conjugate of complex numbers written in this notation. And the complex conjugate is basically what changes is the sign of the imaginary part, so that if my number is z equals 3 plus 4i, the complex conjugate will be 3 minus 4i. Okay, so the imaginary part changes its sign if we are in the notation that is shown here. But in this other notation, what changes is the sign of the phase angle, or the phase, the phase angle as it is known. Now, if you are given a complex number and its complex conjugate, you can work out the magnitude by multiplying the complex number and its complex conjugate and then getting the square root. Okay, so like I give you a complex number, I give you a complex conjugate of that number. If you multiply the two and get the square root, what you get is the magnitude of that complex number. I believe I am clear. And to stop is an assignment that I have given you. It's a simple assignment. You are told find the real and the imaginary part of the complex number. That one. Your answer may include pi. So you are given a complex number and you are asked to find the real part and the complex part, the imaginary part, sorry, the real part and the imaginary part. And I think you just come here and say the real part will be, so you will compute the magnitude and the phase, then you express it in form of the magnitude cos the phase. And the imaginary part, again, you have to compute both the magnitude and the phase. So in that number, you need to identify what is the magnitude and what is the phase, and then you express it as shown in that expression, in those two expressions, for the real part and for the imaginary part. The next part is express that complex number in exponential notation using the Euler's formula. So again, complex in exponential notation. I showed you the exponential notation. Yeah, this is the exponential notation. So where you need to compute the phase as the magnitude and the phase, then you write the complex number in the in this format. So those are two simple assignments that you need to do, and they should be submitted by end of let me say end of Thursday this week. So I will stop at that point, and let's meet next time. Thank you. And before I wind up, we talked with the class rep, and he he told me that we can be starting our class from 8, that is the lecture, and up to 10. Then we have our programming class from 11 to 1. Now, I prefer the class, most of the times I'll be recording my lectures, so the class could be very short, and the class could be short, and basically you ask the questions that if you have any questions, because the lectures will be recorded, and you can always upload, you can always listen to the lectures anytime you want. But the programming classes will have to be there and follow the lesson from 11. Thank you.